Okay, good morning. Welcome to today's class. We are going to continue with self-induction part 2, section B part 2. Okay. Self-induction section B part 2. Okay. We go to question number 2. Yesterday. Okay, we go to question number 2. Okay, number 2A. Explain self-induction in a coil. Okay, explain self-induction in a coil. So we can say that EMF, tapi dia nak explain. Okay, kalau kita explain, okay, boleh pendek je because only 2 marks. Okay, so EMF is induced in one coil due to changing current in the coil itself. Okay. Explain self-induction in a coil. EMF is induced in one coil due to changing current in the coil itself. Right? Then continue with question B. We got an inductance, self-inductance of 2.00 Henry. Connected in series to a battery with EMF of 6.00 volt. A lamp needs minimum voltage of 100 watt to light up. Okay. Then we got a graph of current versus time. Right? Current versus time. Okay, we got current versus time. Okay, okay. Then in this graph, we say that the switch, the switch is closed at t equal to 0 and open at t equal to 1 second. Kalau switch closed, meaning current will, the circuit will be complete, so current will start to flow, will start slowly increasing, the current slowly increasing, and then it will have a constant value. And then when open at 1 second, that means the circuit is being short circuit lah, kan? The circuit is off now, so there will be a drop of current. Okay, so the full question, I read it out because this is only summary. So an inductor of self-inductance of 2 Henry is connected in series to a battery of EMF 600 volt, a lamp of 600 volt, and a vibrating switch. A neon lamp which needs minimum voltage of 100 volt to light up is connected parallel in the inductor. The variation of current following through the inductor with time t is shown in a sketch of the graph below. Okay, right. So the question is number 1. Okay, number 1. Determine the resistance of the inductor. Okay, determine the resistance of the inductor. So V equal to I, R equal to V over I. V is 6 divided by voltage, voltage is 6 volt, and current is 2. Okay, we can see from the graph. The answer is 3.00 ohm. Okay, 3.00 ohm. Okay, if you are done, you can give a thumbs up. Because I want to go on to the next question. Okay, thank you. The question number 2. Okay, I write down here. Can see not? Okay, question number 2. Give a reason for the delay. Okay, give a reason for the delay in the current to achieve the maximum value after switch is closed. Okay. Give a reason for the delay in the current to achieve the maximum value after the switch is closed. When current in the coil is rising, the coil has a changing magnetic flux. Okay, when current in the coil is rising, the coil has a changing magnetic flux. This produces an induced EMF opposite to the battery EMF and causes the delay. Okay. So the reason of the delay in the current to achieve maximum value after the switch is closed is that when current in the coil is rising, the coil has a changing magnetic flux. This produces an induced EMF opposite to the battery EMF and causes the delay. Right? Okay, done. Right, then we go to question number 3 Roman. Okay, number 3 Roman. Sketch a graph of the variation of induced EMF with time. Okay, so this is the induced EMF. Okay, induced EMF with time. This is at 0.50 second. And then starting at 1 second to 1.02 second. Okay, like that, right? Okay, so that is the induced EMF with time. Okay, so we can see that you must make sure that you know how to sketch this graph for induced EMF and also for current. Okay. Right? Right. Okay, question number 4. Question number 4. Based on the graph, based on question number 3, describe how the lamp can be lighted up. Okay, can be lighted up. Okay, based on number 3, describe how the lamp can be lighted up. When the switch is open, at 1 second, the current goes to 0 very fast. The rate of change of current is very high. This produce a very induced EMF, which can light up the neon lamp. Okay. Based on 3, describe how the lamp can be lighted up. So when the switch is open at 1 second, the eye goes to 0 very fast. The rate of change of current is very high. This produces a very high induced EMF which can light up the neon lamp. Okay, question number 5. Calculate the initial rate of change of current when the switch is closed. Calculate the initial rate of change of current when the switch is closed. EMF is equal to negative L di over dt. So we want to find this di over dt. When the switch is closed, the induced EMF is 6 volt. So this is 6 equal to 2, right? 2 di over dt. Okay. Okay. Okay, when you are finished, you can give your thumbs up. Okay. Right. Okay, number 6. Okay, question number 6. Calculate the average induced EMF when the switch calculate the average induced EMF when the switch is open. Right. Then we got our L is 2. And when the switch is open, the rate of change of current, okay, kita tengok. Okay. Jadi ni bila close current is increasing, then constant, no change of current. But when the switch is open, there is a change in current. Okay, from 2 to 0 in the time of 0.02 volt. So we don't have to use this formula. Okay, we just take from the graph. So from the graph, the average induced EMF is okay. And then next question, the maximum energy stored. Okay, the maximum energy stored okay. That's all. Finish the question. So there's a lot of explanation you need to do from the graph, okay, and then calculation. Okay, I continue with question number 3. Okay, question 3. Explain self-induction. Okay, explain self-induction. Okay, this question is like more than 2 marks. Just now, when you explain the self-induction, only 2 marks. So we just say that EMF is induced in one coil due to changing current in the coil itself. That is like 2 marks lah. But this is more than 2 marks. Okay, this is more than 2 marks, meaning you need to explain more lah. Okay, if you answer like just now, EMF is induced in one coil due to changing current in the coil itself, so you get only 2 marks lah. But this is more than 2 marks, so you nak dapat 2 markah sahaja, you boleh jawab pendek macam tadi. If you want more marks, okay, you see the marks how many marks they give you. If more than 2 marks, so you need to explain more. Okay, the step by step. So when current in the coil changes, the magnetic field, okay, the magnetic field produced by the coil changes. When current in the coil changes, the magnetic field produced by the coil changes. Then the magnetic flux of the coil changes. Okay, first current change, then magnetic field produced by the coil changes, then magnetic flux of the coil changes. According to Faraday's law, induced EMF is directly proportional to rate of change of magnetic flux. Okay, therefore there is an induced EMF produced in the same coil. Okay, so for explain self-induction, more than 2 marks. Okay, if more than 2 marks, this is how you explain it. When current in the coil changes, the magnetic field produced by the coil changes. The magnetic flux of the coil changes. According to Faraday's law, induced EMF is directly proportional to the rate of change of magnetic flux. Therefore, there is an induced EMF produced in the same coil. Okay, if you are done, you can give a thumbs up. Right. Okay, B, B. We got a source here, and then we got coil. Then we got a light bulb. Right. So this is the coil. This is the light bulb. Okay. Explain the changes in the brightness of the bulb that could occur when an iron core is inserted into the coil. Okay. Explain the changes in the brightness of the bulb that could occur when an iron core is inserted into the coil. Okay. As iron core is inserted into the coil, the magnetic field by the coil increases. The magnetic flux of the coil changes. According to Faraday's law, an EMF is induced. According to Lenz law, the direction of induced EMF is opposite the EMF of the battery. Hence, the total EMF in the circuit is reduced. Current is reduced. the brightness of the bulb decreases. Okay, as an iron core is inserted into the coil, the magnetic field by the coil increases. The magnetic flux of the coil changes according to Faraday's law, and EMF is induced. According to Lenz's law, the direction of the induced EMF is the opposite to the EMF of the battery. Hence, the total EMF in the circuit is reduced, current is reduced. The brightness of the bulb decreases. Okay, now we go to C. Okay, C. The rate of change of current is 10 as negative 1. Okay. The number of turns of coil is 500 turns. The back EMF is 24.5 millivolt. Okay, A or 1. What is the, calculate the self-inductance? Okay, calculate the self-inductance. Negative L di over dt. Okay, the unit for inductance is Henry. If you are finished, thumbs up. Thank you. Okay, I'm out of paper. Okay, question C2. Okay, C2. Just now C1 lah. Magnetic flux through each turns when current is 4 okay, current is 4.00 ampere. So current is 4. Okay. D inductance is 2.0 Henry. Resistance is 5 ohm. Voltage of the battery is 12.0 volt. Then current is 1.4 ampere. Okay, determine back EMF. Okay, determine the back EMF. Okay, we can use this formula because we got all the information. Okay, number 2, rate of change of current in the coil. Rate of change of current is di over dt. So we are going to use the back EMF. No. We want to find di over dt kan. Okay. So we take the back EMF, put inside this formula. Okay. Right, if you are done, you can give a thumbs up. Okay, thank you. Question number 4. A. State Faraday's law and Lenz law. Okay, write an equation to summarize the two laws. Explain why Lenz law is consistent with the principle of conservation of energy. Okay, state Faraday's law and Lenz law. Okay, kita do one by one. So Faraday's law induced EMF is directly proportional to the rate of change of magnetic flux linkage. Lenz law, the direction of induced current is to oppose the change that producing it. Okay, state Faraday's law, induced EMF is directly proportional to the rate of change of magnetic flux linkage. Lenz law, the direction of induced current is to oppose the change that producing it. And then write an equation to summarize the two laws. Okay, where this is the rate of change of magnetic flux linkage. Okay, Now, explain why Lenz's law is consistent with the principle of conservation of energy. Explain why Lenz's law is consistent. So we draw a coil, then a magnet bar that is pushed into the coil. So our B magnetic flux is increased. Okay, our magnetic flux is increased in this direction. And then we have our B induced in this direction. Okay, that's the diagram. Because they want to use Lenz's law to explain, you need to say the north and the south pole. Okay, when north pole of magnet is pushed into the coil, EMF is induced due to the increase of magnetic flux linkage. Okay, when north pole of magnet is pushed into the coil, EMF is induced due to the increase of magnetic flux linkage. According to Lenz's law, the direction of the induced current in the coil must produce a north pole at the end of the coil facing the magnet. So dekat sini. Okay. Hence, mechanical work has to be done against the mechanical repulsion. The work done is converted to electrical energy, right? Okay, when north pole of a magnet is pushed into the coil, EMF is induced to the increase of magnetic flux linkage. According to Lenz's law, The direction of induced current in the coil must produce a north pole at the end of the coil facing the magnet. Hence, mechanical work has to be done against the mechanical repulsion. The work done is converted to electrical energy. Okay, that is how we explain why Lenz's law is consistent with the principle of conservation of energy. The work done is converted to electrical energy. When we answer, we follow the question need. They say explain by using Lenz's law, so we must have n pole. Okay, and then the principle of conservation energy is from what work to what work. Okay, hand mechanical work has to be done against the mechanical repulsion. The work done is converted to electrical energy. So that is the principle of conservation of energy there. Okay, if you are finished here, give a thumbs up. Right. Okay. Continue with question B. We got an inductance of 55 millihenry, resistance 30 ohm. The voltage of the battery is 6 volt. Number 1, sketch graph of I versus T. After the switch is closed. Explain the shape of the graph. Okay, sketch a graph of current versus T after the switch is closed. Explain the shape of the graph. Okay, then I go on to the next question. On the same axis, draw another graph. Okay, draw another graph. If the inductance of the inductor is greater. Short form. Okay, first you need to sketch the graph and then explain the shape of the graph after the switch is closed. So we know that after the switch is closed, okay, the current will slowly to increase and will reach a consistent current here. Okay, so this is like my number 1 graph. Kan? This is my number 1 graph. Okay, then you explain. So after the switch is closed, I increases slowly. due to the back EMF induced. The back EMF, okay, opposes the increase in current. Okay, after the switch is closed, current increases slowly due to the back EMF induced. The back EMF opposes the increase in current. Then on the same axis, draw another graph if L is greater. Okay, when L is greater, the back EMF is also greater. Okay, the back EMF also greater. So it will reduce the current. So my second answer for the second graph is like the current is not as high as the number 1. Okay, as L increases, okay, as L increases, EMF back also will increase, and we will have a decrease in current. So this is my second graph. Okay, it's lower than the first one. Okay. Okay, number 3. Number 3, maximum current in circuit. Okay, maximum current in circuit. OV equal to IR okay, this is the maximum current in the circuit. Okay, give 2 significant figure answer, because in the question we have 6.0 volt. So 2 significant figure. Okay. Number 4. What is the maximum energy stored? Then name the form energy stored. Okay, formula. Name the form of energy stored is magnetic field. Okay. Okay, if you are done, you can give a thumbs up. Actually, now we are doing section C, kan? So more question for self-inductance is in the essay question. Not much in the subjective question. Okay, so and usually they will combine with Faraday and Lenz law. Okay, so essay question, all this. Okay, question number 5, right? Define self-inductance. Okay, define. When we say we define, so we can use formula. Okay, we can start by writing EMF negative L di over dt. Then L is EMF over di over dt. So this is where EMF is the back EMF, di over dt is the rate of change of current in inductor. Okay, B, this is question number 5. B, we got macam soalan tadi je. Okay, inductance of 5.0 Henry. The battery is 12 volt. Resistance is 6.0 ohm. Number 1. Rate of growth of I at the instant when switch close. Okay, when switch is closed. So we want to find the rate of growth of current when the switch is closed. Yeah, so EMF is equal to negative L di over dt. So this want to find this. EMF is 12 equal to 5 di over dt. (2.4 as negative 1). Okay, no problem. Easy, straightforward question. And number 2, final value of current. Okay, final value of current. Okay, if you are finished, give a thumbs up. Okay, thank you. Now if you we continue with number 3, yeah. Number 3, energy stored. When current is maximum. Okay, when current is maximum. Okay, and number 4, mean induced EMF when switch is open. If current falls to 0 in 0.2 seconds, sketch a graph of current against time, the instant the switch is closed until it is open again. Okay. Calculate the mean induced EMF when the switch is open. When the switch is open, the final is 0 and maximum is now is 2 within 0.2 seconds. Okay? And then sketch a graph. Okay, sketch a graph of I against time from the instant the switch is closed until it's open again. So we've done many of the exercises here. Sketch I over T times T, and then the current when is closed, switch is closed, the currents will increase until it become maximum constant. So maximum is 2. Okay, become constant, and then when the switch is closed, it will drop quickly. Okay, it will drop quickly. So this time here is within 0.2 seconds. Okay. So that's how we sketch the graph. Okay. Okay, class. If you are done, you can give thumbs up. Okay, so we end our class today. That's all. Thank you. Bye bye.